Hey guys, this is the last section on equilibrium, and it's called Applications of Equilibrium Constant. So we spent last week learning about the KEQ equation, so we could do it for concentrations or for pressure. But what does that tell us? So we're going to look at something today called the reaction quotient, which is a capital Q for our reaction quotient. So it's basically the same ratio the equilibrium expression gives. So it's the products over the reactants, but it's for a system that's not at equilibrium. So to calculate Q, one is going to substitute the initial concentrations in reactants and products into the equilibrium expression. So we're still going to set up an expression of Kc equals the concentration of products over the concentration of reactants, okay? Just like we would, except when we do this one, this has to be at equilibrium. Q can be calculated at any point in a problem. So if Q equals K, so if those things are the same, that means the system is at equilibrium. So what we were actually calculating is the K. So that's the scenario here. If they're the same, the system is at equilibrium. If they're not the same, that gives us information about which way the system needs to shift in order to reach equilibrium or go back to equilibrium. So if Q is greater than K, that means there's too much product and the equilibrium shifts to the left. So if Q is greater than K, that means that there's too much product. We need to shift back to the reactants in order to reach equilibrium, which makes sense. If it's bigger, that means the numerator number was larger. If Q is less than K, so this scenario here, that means there's too much reactant. The denominator was larger, and so we need to shift to the right and make more product in order to get to equilibrium. Okay, so let's look at an example of this. For the Haber process, the equilibrium constant is 0.105 at 472 degrees Celsius. Suppose we place 2 moles of H2, 1 mole of N2, and 2 moles of NH3 in a 1 liter container at 472 degrees Celsius. How will the mixture react to reach equilibrium? Which way will the reaction proceed? Okay, so we know that this is the Kc value. So that's what we're going to compare it to. So Q, and you guys, the Haber process is N2 plus H2 gives us NH3. Hopefully we know this at this point. Get it balanced out there. So Q is going to be equal to NH3 squared over N2 and H2. So remember, the brackets mean concentration. So we're putting 2 moles of H2. Moles is not a molarity, but we're in a 1 liter container. So 2 divided by 1 stays at 2. So we've got, let's see, 2 molar H2. That'll be cute. We've got 1 molar N2. And we have 2 molar NH3. Okay, so 2 squared is 4. 2 cubed is, so 2 times 2 is 4. 4 times 2 is 8. Times 1 is 8. So 4 over 8 is 1/2, or 0.500. So that is Q. So in this case, if we look and we compare our Q and our Kc value, Q is greater than Kc. Since it's bigger, that means that there must be more product. And so we need to shift to reactants, which is to the left. Let's try one more. You guys try it, and then check your answer. Okay, so one reminder is that we're given values in moles, but we're in a 2-liter container. So make sure that you take each of those values divided by 2. And what I found was Q equals 1.33. So if we're comparing our Q and our Kc, Q in this case is less than our Kc, which means that we had more reactant. So it is going to shift to the products, which is to the right. Okay, so one more thing about equilibrium is the effects of catalysts on equilibrium. And we know that catalysts speed up a reaction by decreasing the amount of energy or the activation energy required. So when we put catalysts in, catalysts increase the rates of both the forward and the reverse reaction. So we can see that if this pink one is our uncatalyzed reaction, we've got a higher activation energy. Remember, top to bottom, that's our activation energy from last chapter. And so the catalyst is the green line, and basically it lowers that activation energy, which makes it easier and faster for this reaction to occur. And so what we can see that it does to equilibrium is it reaches equilibrium faster, but it doesn't change any of the equilibrium compositions or concentrations. So when we look at this graph here, which is our concentration, the pink line again is without a catalyst, and it takes quite a while for it to reach that equilibrium concentration where it remains constant. The green line is with a catalyst, and you can see that the concentration change in the beginning is much more rapid and it reaches equilibrium faster. So it's still the same concentration at equilibrium. It doesn't affect that at all. It just affects how quickly we actually reach equilibrium.